Today we're talking about what happens when our eigenvalues are complex. So just as a reminder, whoops, geez, I seem to be doing that a lot. Starting off with the wrong color marker there. So we have ax1 plus bx2, x2 prime equals cx1 plus dx2. And so we have formulated our two equations that we need to solve. Right, we've taken our the determinant, set that equal to 0, and now lambda is equal to the trace of a plus or minus the square root of the trace of a squared minus 4 times the determinant of a divided by 2, because you remember that this turns out to be lambda squared minus the trace of a times lambda plus the determinant of a equals 0. Good. All right. So what I'm saying here is that we're going to assume that lambda is alpha plus or minus beta I. Okay? And so you could even be more specific if you wanted to. Lambda is alpha over 2. Oops, sorry. It's the trace over 2. Let me say that again. Alpha is the trace of a divided by 2. And then beta is equal to, I'm going to reverse these, or you could say negative, the trace of a squared minus 4 times the determinant of a. Take the square root, divide by 2. Okay, because of course trace is squared minus 4 times the determinant is negative, right? So we're making that positive. Good. So as it turns out in our solution, if lambda is equal to e, let me rewrite that. If e to the lambda t is e to the alpha plus beta I times t, then that's equal to e to the alpha t times e to the I times beta t. And so that's e to the alpha t cosine beta t plus I sine beta t. Okay, so as we're going to find out, if I'm wondering if my solutions are staying bounded or if they're going to infinity, it really depends on this piece, right? Because this piece just spins us around the axis. And so what we're going to see is we're going to be talking about the real part of our lambda and our imaginary part of lambda. Okay, but I've gotten ahead of myself. Let's go back to our e to the lambda t here, and the solution to the system is given by x of t equals the real part of e to the lambda t times eigenvector v plus, oops, I forgot my c1, c2 times the imaginary part of e to the lambda t times v. Okay? So you only have to work with one lambda, and then we also have to compute our eigenvector. Alright, so compared to chapter 3, if you compare to chapter 3, we said that y of t is c1 times the real part, oops, c1 times the real part of e to the rt plus c2 times the imaginary part of e to the rt. So all we're doing to go from chapter 3 to chapter 7 is really just adding this eigenvector v in. Okay, and so the proof of this is actually pretty straightforward. It's actually mimicking the proof of the one from chapter 3. So I'm not going to go into the proof. We'll just take a look to see how this is computed, and then we'll take a look at how it's graphed. Okay, so let's just start off with an example. Suppose I've solved for the eigenvalue and the eigenvector, and I found that lambda equals 1 plus 2i, and the eigenvector v is 1 and 1 plus I. Okay, so how do I formulate my solution? I take e to the lambda t times v, and I multiply it out. So that's e to the 1 plus 2i t times 1 plus I. Keep going. E to the t, e to the I, 2t times 1 plus I. Keep going. That's equal to e to the t times cosine 2t plus I sine 2t times 1 plus I. And now we have to FOIL that out, so that's e to the t, and then the vector is, this one's just going to be cosine of 2t plus I sine of 2t. But then this one is going to be, if I FOIL it out, cosine of 2t times 1 is cosine of 2t. And then to get the other part of the real, or the other real part, I would have I sine times I. That would be I squared times sine, which is minus sine of 2t, plus I. Now I'm looking for the imaginary part, so I get a cosine of 2t. And then the other one would be coming from plus. Oops, I've already got the I out there. Sine of 2t. Okay, and so this is the solution now, the general solution, and now I want to get my x of t. X of t is equal to c1 times e to the t, and then I just take the real part for the first, try to get my penmanship going here. I'm moving around for some reason. Cosine of 2t minus the sine of 2t plus c2e to the t sine of 2t. Whoop! Went right off the side. 2t over cosine of 2t plus sine of 2t. And one thing you'll notice here is that this solution has no I in it, right? There's no I. Okay, so this is the real solution. Very good. So what does this look like? Well, the sine and cosine terms, like I was saying before, they're going to rotate you in the plane, and then the exponential term is going to expand our solution. So what's going to happen is that the solution will spiral out, either like this. I could spiral out that way. Am I going in? Did I do that right? Yep. Or it could be spiraling the other way, right? So I could have a clockwise or counterclockwise. This is counterclockwise. This is clockwise rotation. And in order to determine that, we actually have to have the original matrix. But in both cases, you'll notice that we're spiraling outwards, and the direction is outwards because of the e to the t. And so we would classify our equilibrium, classify the origin, the stability of the origin, is a spiral source in this case. We would call this a spiral source. We wouldn't be able to get more specific than that right now because we don't have access to the matrix. We just have, I just gave you the eigenvalue and the eigenvector up at the top. Okay, so in another problem where we actually have the matrix, we'll plot the solution directly. Okay, so that's how you actually do the computations. So again, just to reiterate here, what happens if we have complex eigenvalues? We only need one complex eigenvalue and then find the eigenvector, and then you compute the real part of e to the lambda tv, the imaginary part of e to the lambda tv. Those are your two pieces to your solution. Okay, so it's almost 10 minutes. I'm going to stop it here, and then we'll look at a specific example from start to finish from the matrix instead of just from the eigenvalue and eigenvector. See you then.